Welcome to Sleeping Researcher, where science narration gently guides you into restful sleep. Here, we explore the wonders of the universe with a calm voice and a peaceful pace, helping your mind relax as you drift off. Today, we embark on a serene journey through one of the most fascinating forces in nature, gravity. Gravity is the invisible thread that holds the cosmos together, gently pulling planets, stars, and galaxies into a cosmic dance. But gravity is more than just a simple force of attraction. Massive cosmic events like the collision of black holes or the explosive death of stars warp the very fabric of space-time itself. This warping creates ripples that travel across the universe, shaping the way everything moves and exists. As we explore how these colossal events bend and stretch space-time, you will discover a universe that is dynamic, alive, and endlessly mysterious. Together, we will unfold the quiet power behind gravity's influence and the cosmic stories it tells. If you enjoy this calming exploration of the universe, please like the video and subscribe to Sleeping Researcher. Your support helps us continue to bring soothing science narration to your nights. Now, let us gently delve into the graceful folds of space-time and the majestic force we call gravity. Imagine a gentle, invisible thread that connects everything in the cosmos, pulling stars, planets, and galaxies into an intricate cosmic dance. This thread is gravity, the fundamental force that quietly shapes the structure and behavior of our universe. It is not merely a force that keeps our feet firmly planted on the earth or causes apples to fall from trees. Gravity is the cosmic architect, governing the motions of celestial bodies and guiding the evolution of the vast cosmic web. From the tiniest particles to the grandest galactic clusters, gravity weaves the fabric of the universe, orchestrating a harmony that spans billions of light years. It is through understanding gravity that we begin to grasp the elegant simplicity and profound complexity of the universe we inhabit. Gravity's influence extends far beyond everyday experiences. It is a universal force of attraction that pulls objects with mass toward one another. The more massive an object, the stronger its gravitational pull. This principle explains why planets orbit stars, moons circle planets, and galaxies cluster together. However, gravity is not simply a force acting at a distance. It is intimately connected with the very fabric of space and time. According to Einstein's theory of general relativity, gravity arises from the warping or curvature of space-time caused by the presence of mass and energy. Imagine space-time as a vast, flexible sheet. When a massive object, like a star or black hole, rests upon this sheet, it creates a depression or warp that influences the paths of nearby objects. They naturally follow the curved contours of space-time, resulting in what we perceive as gravitational attraction. This profound insight reshaped our understanding of gravity from a mere force to a geometric property of the universe. Massive cosmic events, such as the collision of black holes or the explosive death of stars dramatically warp space-time in ways that ripple across the cosmos. When two black holes spiral inward and merge, they create powerful disturbances in space-time known as gravitational waves. These waves propagate outward at the speed of light, stretching and compressing space as they pass through, much like ripples on a pond's surface. Although these waves are incredibly subtle by the time they reach Earth, advanced observatories have now detected them, providing a new way to observe the universe. Such events reveal the dynamic and ever-changing nature of space-time itself, showing that gravity is not static, but a vibrant, moving fabric shaped by the most extreme phenomena. Through these cosmic interactions, we gain a deeper appreciation for gravity's role beyond just attraction. It is a bridge connecting the geometry of space-time with the energetic dance of celestial bodies. As we continue to explore and unravel the mysteries of gravity, we see how it sets the stage for everything from the formation of galaxies to the evolution of life on Earth. By understanding how mass and energy warp space-time, scientists can predict the motion of planets, the behavior of stars, and the fate of the cosmos itself. Gravity's subtle yet powerful influence binds the universe together in a complex tapestry of cause and effect. This foundational force invites us to look deeper into the nature of reality, inspiring curiosity and wonder about the unseen forces that govern existence. With this understanding of gravity's essential role, we are now poised to delve further into the ways massive cosmic structures shape the universe's grand design. Gravity is a force that touches every aspect of our daily lives, from the simple fall of an apple to the majestic orbits of planets around their stars. This invisible pull, first famously observed by Isaac Newton when he contemplated the falling fruit, reveals a profound truth. Every object with mass attracts every other object. While the apple's descent may seem ordinary, it echoes the same principles that govern the paths of celestial bodies millions of kilometers away. This connection between the familiar and the cosmic invites us to see gravity not just as a mundane force, but as a fundamental thread weaving together the universe. It is through this lens that we find a sense of continuity, linking our own experience with the vast and intricate dance of planets, moons, and stars. As we reflect on this, gravity's reach extends far beyond the Earth, shaping the motions of countless worlds and guiding the motion of the heavens with a gentle, persistent hand. At the heart of gravity's influence lies the elegant concept of space-time, the four-dimensional fabric in which mass and energy reside. Massive objects such as planets and stars cause this fabric to curve around them, much like a heavy ball resting on a stretched sheet of rubber. This curvature is not a mere analogy, but a real distortion that dictates how objects move, pulling smaller masses along paths shaped by the bends and dips. When we witness a planet orbiting a star, we are seeing the effects of this warping as the planet follows a path curved by the star's mass. Even light, which travels at an incredible speed, must adjust to these contours, bending as it passes massive bodies in a phenomenon known as gravitational lensing. This dynamic interplay between mass and space-time reveals a universe that is far from static, but a living, breathing expanse shaped by the presence and movement of matter. By embracing this perspective, we begin to appreciate gravity as a sculptor of cosmic landscapes, crafting the very structure of reality. When we turn our gaze to the most massive and energetic events in the cosmos, the warping of space-time becomes even more dramatic and profound. Cataclysmic occurrences such as the collision of black holes or the explosive death of massive stars ripple through space-time, sending gravitational waves that travel vast distances across the universe. These waves are subtle distortions, like ripples on a pond surface, but they carry invaluable information about the violent events that created them. Observatories on Earth have begun to detect these faint signals, opening a new window into the cosmos and allowing us to witness phenomena that were once purely theoretical. The immense gravitational fields around supermassive black holes bend and twist space-time to such extremes that time itself slows down near their event horizons. These cosmic giants serve as natural laboratories for understanding gravity's most intense effects, pushing the boundaries of physics and deepening our knowledge of the universe's fundamental workings. Through these extraordinary events, we see gravity not only as a force of attraction, but as a messenger, conveying the stories of the universe's most powerful moments. From the simple pull that brings an apple to the ground, to the vast gravitational waves echoing across the cosmos, gravity remains a constant presence, shaping the very fabric of existence. Its influence extends seamlessly from the intimate scale of our everyday lives to the incomprehensible grandeur of cosmic phenomena. This remarkable continuity allows us to connect the tangible with the abstract, grounding our understanding of the universe in experiences both familiar and awe-inspiring. As we continue to explore these connections, we find ourselves drawn deeper into the mysteries of space-time and the role gravity plays in the grand cosmic dance. With each new discovery, we edge closer to comprehending the delicate balance that governs the cosmos, inviting us to journey further into the fascinating realm of gravitational phenomena. In the late 17th century, Sir Isaac Newton formulated a principle that would become the cornerstone of classical physics: Newton's law of universal gravitation. This law elegantly describes how every mass exerts an attractive force on every other mass, a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. It was a profound revelation, offering a simple mathematical relationship that explained not only why objects fall toward Earth, but also how the Moon orbits our planet and how the planets circle the Sun. Through this lens, gravity became a universal force, invisible yet powerful, binding together the vast complexity of the cosmos in a harmonious dance. Newton's insight bridged the tangible world of everyday experience with the celestial mechanics of the heavens, allowing us to predict motions with remarkable precision and laying the groundwork for centuries of scientific exploration. Yet, as our understanding deepened, it became clear that Newton's law, while precise and enduring, was only part of a larger story. It treated gravity as a force acting at a distance, instantaneous and invisible. An idea that worked well for most practical purposes, but left unanswered the profound questions about the nature of space and time themselves. This realization set the stage for a revolutionary shift in perspective, one that would reimagine gravity not as a force, but as a curvature of space-time. Still, Newton's law remains a remarkable testament to human curiosity and intellect, providing a foundation from which we continue to explore the intricate tapestry of gravitational interactions that govern the universe. It invites us to consider how gravity connects every particle and planet, a silent architect shaping movement and structure across unimaginable scales. As we look beyond the familiar scope of Newtonian gravity, massive cosmic events reveal a more complex and fascinating dimension to this fundamental interaction. When enormous bodies like black holes or neutron stars collide or merge, they create ripples in the fabric of space-time itself, known as gravitational waves. These waves travel across the cosmos at the speed of light, carrying information about the most extreme environments in the universe. Such phenomena warp space-time profoundly, bending and stretching it in ways that transcend classical descriptions. The remarkable detection of these waves in recent years has opened a new window into the universe, allowing us to observe the unseen and understand the dynamic interplay of gravity on a cosmic scale. This profound warping caused by massive events not only shifts how we perceive gravity, but also deepens our appreciation for the elegant complexity woven into the universe's very structure. By embracing both the classical insights of Newton and the revolutionary concepts introduced by modern physics, we begin to glimpse the true nature of gravity as a fundamental interaction that shapes the cosmos from the smallest scales to the grandest. The warping of space-time triggered by massive cosmic events challenges us to expand our understanding beyond forces and motion, inviting us to explore the geometry of the universe itself. As we continue this journey, the interplay between mass, energy, and the curvature of space-time unfolds a narrative as profound as it is beautiful, guiding us toward deeper mysteries that await beyond the horizon of current knowledge. With every step, gravity reveals itself not just as a force, but as a language written into the very fabric of existence. Newtonian gravity, with its elegant simplicity, has long served as the foundation for understanding the motion of planets, moons, and everyday objects on Earth. According to Newton's law of universal gravitation, every mass exerts an attractive force on every other mass, proportional to their masses and inversely proportional to the square of the distance between them. This framework successfully explains a wide range of phenomena, from the orbits of planets to the tides, and remains remarkably accurate for many practical purposes. Yet, as scientists probed deeper into the cosmos and observed phenomena involving extremely massive bodies or velocities nearing the speed of light, subtle discrepancies began to emerge. These deviations hinted at the need for a more comprehensive description, one that could account for the intricate dance between mass, energy, and the fabric of space itself. Newton's theory treats gravity as a force acting instantaneously across a distance, which works well at human scales, but fails to capture the complexities of the universe at large scales and high energies. This limitation became increasingly apparent as astronomers observed the behavior of light and matter near massive objects, and as they sought to understand the origins and evolution of the cosmos. The advent of the 20th century brought with it a profound shift in our understanding of gravity, with Einstein's theory of general relativity. Unlike Newton's concept of gravity as a force, Einstein proposed that gravity arises from the curvature of space-time itself, a four-dimensional fabric that melds space and time into a single continuum. Massive objects like stars and black holes cause this fabric to bend and warp, much like a heavy ball placed on a stretched rubber sheet. This curvature directs the paths along which objects and light travel, replacing the notion of a mysterious force with a geometric explanation. When massive cosmic events occur, such as the collision of black holes or the explosion of supernovae, they create ripples in space-time known as gravitational waves. These waves propagate through the universe at the speed of light, carrying information about some of the most energetic processes in existence. This revolutionary perspective not only resolved the inconsistencies observed in Newtonian gravity, but also opened new vistas for exploring phenomena that had remained elusive for centuries. Despite its successes, general relativity too has its boundaries, especially when confronted with the quantum realm or the conditions near singularities, points where density and curvature become infinite, as theorized at the centers of black holes or at the birth of the universe itself. In these extreme environments, the smooth fabric of space-time predicted by Einstein's equations is thought to break down, signaling the need for a theory that unifies gravity with the principles of quantum mechanics. These limitations encourage ongoing research into quantum gravity and other approaches that seek to reconcile the macroscopic and microscopic worlds. Yet, even within its domain of applicability, general relativity has profoundly transformed our conception of gravity from a mere force to a dynamic interplay between matter and geometry. This shift challenges us to rethink the universe not as a static stage, but as a living, evolving entity, shaped by the invisible contours of space-time. As we look beyond the classical paradigms, the warping of space-time by massive cosmic events invites us to explore new horizons, where the familiar laws give way to deeper, more subtle interactions. The dance of galaxies, the bending of light around massive clusters, and the echoes of gravitational waves all trace the contours of a universe shaped by gravity's geometric essence. Each discovery propels us closer to understanding the full tapestry of cosmic gravity, one woven from the threads of mass, energy, and the curvature of space-time itself. This unfolding narrative beckons us forward, inviting contemplation of phenomena that stretch the limits of our imagination and the boundaries of our scientific frameworks. At the dawn of the 20th century, Albert Einstein introduced a profound shift in how we understand gravity. Moving beyond the Newtonian notion of a force acting at a distance, Einstein proposed that gravity arises from the very geometry of the universe itself. His theory of general relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Imagine space and time as a flexible fabric that bends and warps in response to the presence of matter. When a massive object, like a star or a black hole, sits on this cosmic fabric, it creates a dimple, gently pulling nearby objects along curved paths. This revolutionary perspective reframes gravity as a geometric phenomenon, fundamentally altering our comprehension of the cosmos. The elegance of this framework lies in its ability to unify space and time into a single continuum, where the flow of time itself can be influenced by gravitational effects. Einstein's insight opened new pathways for exploring phenomena that classical physics could not adequately explain, setting the stage for a deeper understanding of the universe's intricate architecture. The impact of general relativity extends far beyond mere theoretical elegance. It provides a predictive lens through which we observe the cosmos. One of the most striking confirmations of Einstein's theory came from the bending of light around massive celestial bodies, a phenomenon known as gravitational lensing. When light from distant stars or galaxies passes near a massive cluster, the curvature of space-time bends the light's path, creating arcs, rings, or multiple images. This cosmic mirage not only confirms the warping of space-time, but also serves as a powerful tool for astronomers to map the distribution of both visible and invisible matter. Similarly, the theory predicts the existence of gravitational waves, ripples in the fabric of space-time caused by cataclysmic events such as merging black holes or neutron stars. The detection of these waves has opened an entirely new window into the universe, allowing us to listen to the echoes of cosmic collisions and witness the dynamics of gravity in its most extreme forms. Each observation enriches our understanding and affirms the profound truth that gravity is woven into the very geometry of space and time. Massive cosmic events do more than simply attract objects. They sculpt the contours of space-time on scales both grand and subtle. Black holes, with their immense density, create regions where space-time curves so steeply that not even light can escape, defining the mysterious event horizon. Neutron stars, remnants of supernova explosions, pack incredible mass into a tiny volume, curving space-time and warping time itself in their vicinity. Even on the vast scales of galaxy clusters, the collective mass bends space-time and shapes the motion of galaxies, guiding the cosmic web's grand architecture. This dynamic interplay between mass and geometry reveals a universe in constant dialogue, where energy and matter imprint their presence on the very fabric that supports existence. Understanding these interactions not only deepens our grasp of gravity, but also challenges us to rethink the nature of reality itself, bridging the abstract with the tangible in a cosmic ballet of form and function. To truly understand gravity, we must first embrace the concept of space-time, a seamless four-dimensional fabric where the dimensions of space and time intertwine. In everyday experience, we perceive space as the three dimensions through which we move: length, width, and height, while time flows independently, marching forward at a steady pace. However, physics reveals a deeper, more unified structure where space and time are inseparable, forming a single continuum. This fabric is not merely an abstract idea, but the very stage upon which all physical events unfold. It stretches and bends in response to the presence of matter and energy, shaping how objects move and how time passes. When massive bodies, like stars or planets, occupy this cosmic fabric, they create dents and curves, much like a heavy ball placed on a taut rubber sheet, altering the paths of anything nearby. This analogy, while simplified, captures the essence of how gravity operates, not as an invisible force pulling objects directly, but as a manifestation of curved space-time guiding their motion. Understanding this fusion of space and time is essential because it shifts our perspective from a world governed by forces acting at a distance to one where geometry dictates the dance of the cosmos. The four dimensions of space-time extend beyond our immediate senses, inviting us to imagine a universe woven together with threads of both spatial extent and temporal flow. Events in the universe are not isolated points in space or moments in time, but are anchored to specific locations within this four-dimensional tapestry. When we consider massive cosmic events, such as the collapse of a star into a black hole, their profound impact becomes evident in how they contort space-time locally. This curvature changes the very rules by which objects move, bending the trajectories of passing particles and even the paths of light itself. As a result, light can be trapped or deflected, and clocks near massive bodies tick more slowly relative to those farther away, phenomena predicted by Einstein's theory of general relativity and confirmed by precise measurements. These effects are subtle in everyday life, but become dramatic near extreme masses, revealing the intimate link between gravity, geometry, and time. Thus, space-time is not a passive backdrop, but an active participant in the cosmic story, constantly shaped and reshaped by the matter it contains. The notion of space-time as a dynamic fabric also illuminates the interconnectedness between mass, energy, and geometry. When cosmic events occur, whether the collision of neutron stars or the merging of galaxy clusters, they send ripples through this fabric, much like waves spreading across a pond's surface after a stone is cast. These ripples, known as gravitational waves, travel vast distances, carrying with them information about the violent processes that created them. Detecting these waves has opened a new window into the universe, allowing us to observe phenomena invisible to conventional telescopes. It is through this lens that we appreciate the profound influence of mass and energy, not just as sources of gravity, but as sculptors of the cosmic arena itself. The continuous dialogue between matter and space-time reveals a universe alive with motion and change, where geometry and gravity are two sides of the same cosmic coin. As we delve deeper into this concept, we begin to see that understanding space-time is essential to unlocking the mysteries of the universe's most powerful events and the fundamental nature of reality. To picture how massive objects influence space-time, imagine a vast, flexible sheet stretched taut. When a heavy ball is placed on this sheet, it creates a gentle indentation, a dip where the fabric curves downward. In the cosmos, planets, stars, and especially black holes act much like that ball, warping the fabric of space-time around them. This curvature is not merely a metaphor, but a real, measurable effect that shapes the paths objects take as they move through space. Rather than thinking of gravity as a force pulling objects directly, it is more accurate to see it as objects following the curves and slopes created by mass and energy in the space-time fabric. This visualization helps us understand why planets orbit stars and why light bends around massive bodies, an effect known as gravitational lensing. The more massive the object, the deeper and more pronounced the dent it creates, influencing the motion of everything nearby in subtle yet profound ways. As we consider stars, their tremendous mass warps space-time, guiding the intricate ballet of planetary systems. Our own sun's presence shapes the orbits of planets, keeping them in a delicate balance as they revolve around it. When we turn our gaze toward black holes, these regions of space reveal an even more dramatic distortion. Black holes represent points where mass is so densely concentrated that the curvature of space-time becomes extreme, creating deep wells from which nothing, not even light, can escape. This intense warping affects the trajectory of nearby matter and radiation, often forming spectacular phenomena like accretion disks and powerful jets. Observing these effects allows scientists to glean insights into the behavior of matter under extreme conditions and the very nature of gravity itself. The warping of space-time by such massive objects is a fundamental aspect of the cosmic landscape, shaping the structure and evolution of galaxies and clusters. In addition to static indentations, massive cosmic events can cause dynamic distortions, sending ripples through the fabric of space-time itself. When colossal bodies like neutron stars collide or black holes merge, they produce bursts of gravitational waves, vibrations that travel outward at the speed of light. These waves temporarily stretch and compress space-time as they pass, offering a unique signal from the most energetic processes in the universe. Detecting gravitational waves requires exquisitely sensitive instruments, yet their discovery has revolutionized astrophysics, confirming predictions made by Einstein's theory of general relativity. By analyzing these waves, researchers can probe conditions that are otherwise inaccessible, such as the properties of matter at nuclear densities or the behavior of gravity in its most extreme form. The warping of space-time thus combines both the steady influence of massive bodies and the fleeting echoes of cosmic cataclysms, weaving a complex and dynamic tapestry. This intricate relationship between mass, energy, and the geometry of space-time invites us to reconsider our place within the cosmos. The motions we observe, from the gentle orbit of a moon to the violent merger of black holes, all emerge from the contours shaped by mass. These contours guide not only matter, but also the flow of light and time itself, revealing a universe where gravity is geometry in motion. As our instruments and theories advance, we continue to uncover new layers of this profound interaction, deepening our understanding of the fundamental forces that govern existence. Moving forward, we can explore how these concepts illuminate not just the large-scale structure of the universe, but also the subtle interplay of gravity with quantum phenomena. To grasp the mysterious nature of gravity and how massive events warp space-time, it helps to envision a simple yet powerful analogy: the rubber sheet model. Imagine a taut, flexible sheet stretched out flat. This sheet represents the fabric of space-time, a four-dimensional stage where all cosmic events unfold. When a mass such as a planet or star is placed upon this sheet, it creates a depression or a curve, much like a heavy ball resting on a stretched membrane. This curvature is not merely a visual effect, but a fundamental distortion that influences how objects move nearby. Smaller objects, like marbles rolling across the sheet, are drawn toward the heavier mass, not because of an invisible force pulling them directly, but because they are following the curved paths laid out by the warped fabric beneath them. This simple model allows us to intuitively understand how gravity is not a force exerted across empty space, but rather a geometric property of space-time itself. Extending this analogy, consider what happens when an extremely massive event occurs, such as the collision of two black holes or the explosion of a supernova. These cosmic phenomena drastically deform the rubber sheet, creating ripples that radiate outward. These ripples represent gravitational waves, disturbances in the fabric of space-time itself. As they propagate, they carry energy across vast distances, subtly altering the geometry through which light and matter travel. In the real universe, such events generate waves so faint that only the most sensitive instruments can detect their passing. Yet their existence confirms a dynamic, ever-changing cosmos, where space-time is not static, but responsive, bending and stretching in reaction to mass and energy. The rubber sheet analogy, though simplified, beautifully captures this dynamic interplay, helping us visualize how massive cosmic events can shape the very geometry of the universe. While the rubber sheet provides a tangible way to imagine space-time curvature, it is important to remember its limitations. Space-time itself extends in 4 dimensions, 3 of space and 1 of time, making the true nature of curvature far more complex than a 2-dimensional sheet can depict. Nevertheless, the analogy serves as a gateway to deeper comprehension, inviting us to see gravity not as a mere attraction, but as paths defined by curved geometry. In this curved space-time, objects move along the straightest possible lines called geodesics, which appear as orbits or trajectories influenced by the presence of mass. The more massive an object, the deeper the curve it carves, and consequently, the stronger its gravitational influence. This perspective transforms our understanding of the cosmos, revealing a universe where geometry and gravity are inseparable, and where the dance of celestial bodies is choreographed by the subtle warps of space-time itself. As we refine our understanding of these concepts, the rubber sheet analogy continues to guide our intuition. It bridges the gap between abstract mathematical descriptions and our everyday experience, allowing us to appreciate the profound effect mass has on the fabric of reality. This model also opens pathways to exploring how gravity interacts with other fundamental forces at the smallest scales, a frontier where quantum mechanics and general relativity converge. By contemplating the ripples and curves on this cosmic sheet, we prepare to delve deeper into the mysteries that lie at the intersection of gravity and the quantum world, illuminating the subtle, intricate fabric of existence itself. With this foundation, we can now turn our attention to how space-time curvature reveals itself in phenomena both vast and minute. When we speak of gravity, we often think of the invisible force that pulls objects toward one another, keeping planets in orbit and anchoring us to the Earth. Yet, gravity does far more than merely influence the paths of celestial bodies. It reaches into the very flow of time itself. This phenomenon, known as gravitational time dilation, emerges from the elegant theory of general relativity, which describes gravity not as a force, but as a curvature of space-time caused by mass and energy. In regions where gravity is stronger, such as near a massive star or black hole, time itself slows down relative to areas of weaker gravitational influence. This effect is not just theoretical. It has been confirmed by precise experiments, including those involving atomic clocks placed at different altitudes on Earth, where clocks closer to the planet's surface tick more slowly than those higher above. Gravitational time dilation reveals that time is not an absolute backdrop, but a dynamic dimension, intertwined with space and influenced by the presence of mass. Massive cosmic events, such as the collision of neutron stars or the formation of black holes, offer profound illustrations of how space-time warps under extreme conditions. These events create intense gravitational fields that dramatically curve space-time, stretching and compressing it in ways that challenge our everyday understanding of distance and duration. In the vicinity of a black hole, for example, the gravitational pull becomes so intense that time nearly stands still compared to an observer far away. Photons escaping from this environment lose energy and shift toward longer wavelengths, a process known as gravitational redshift, which further underscores how gravity molds the flow of time and light. The insights gained from studying these colossal phenomena not only deepen our grasp of gravity's nature, but also enhance our understanding of the universe's evolution and the limits of physical laws. These cosmic laboratories enable scientists to test the boundaries of Einstein's theory and to explore the intersection where gravity might reconcile with quantum mechanics. The interplay between gravity and time becomes even more fascinating when considering the fabric of space-time as a flexible four-dimensional entity. Massive objects tell space-time how to curve, and in turn, this curvature tells objects how to move, including the progression of time itself. This dynamic relationship means that the passage of time can vary dramatically, depending on one's position within the gravitational landscape of the cosmos. Near a massive object, seconds might stretch longer, while far from such influences, time flows more freely. Such effects have practical implications beyond theoretical physics. For instance, the global positioning system relies on adjustments for gravitational time dilation to provide accurate location data. This subtle warping of time enriches our appreciation of the universe's complexity and invites us to reconsider the very nature of temporal experience. As we continue to unravel the mysteries of gravity's effect on time, we approach phenomena that challenge the limits of human perception and the frontiers of modern physics. Among the most compelling manifestations of gravity's profound influence on spacetime are black holes, regions where gravity's pull grows so intense that nothing, not even light, can escape. These cosmic phenomena arise from the remnants of massive stars that have exhausted their fuel and collapsed under their own weight. In this collapse, the fabric of spacetime bends to an extraordinary degree, creating a well so deep that it effectively traps all matter and radiation within its event horizon. This boundary marks the point of no return, beyond which the conventional rules of physics give way to the enigmatic. Black holes represent the ultimate extremes of space-time warping, where our understanding of gravity stretches to its limits. Studying these objects offers a glimpse into the universe's most intense gravitational environments and challenges scientists to refine their theories about the nature of space, time, and matter. The warping of space-time around black holes is not merely a theoretical curiosity. It has observable consequences that deepen our understanding of gravity. Surrounding many black holes is an accretion disk, a swirling maelstrom of matter spiraling inward, heated to extraordinary temperatures as it succumbs to the black hole's immense gravitational embrace. In these regions, time itself behaves differently, slowing dramatically compared to an observer far away. This effect, known as gravitational time dilation, means that clocks near a black hole tick more slowly, revealing gravity's intimate connection with temporal flow. Moreover, the immense curvature of space-time can bend light paths, leading to phenomena such as gravitational lensing, where the light from distant stars and galaxies is distorted into arcs and rings. These spectacular effects serve as evidence of the deep relationship between mass, gravity, and the geometry of space-time. They also provide crucial tests for Einstein's theory of general relativity under conditions of extreme gravity. Beyond the event horizon lies the singularity, a point where density and curvature become infinite according to classical physics. Here, the known laws of physics cease to function in their usual form, presenting one of the greatest mysteries in modern science. The singularity is a boundary between our current understanding and the unknown, inviting theories that venture beyond general relativity, such as quantum gravity. The study of black holes thus serves as a bridge between the macroscopic realm of gravity and the microscopic world of quantum mechanics. By peering into these cosmic abysses, physicists hope to uncover a more unified description of the universe, one that reconciles gravity with the quantum forces that govern matter and energy. This quest to comprehend the deepest warping of space-time continues to inspire new ideas and technologies that expand our cosmic horizons. Surrounding the singularity is the event horizon, an invisible boundary in space-time that marks the point of no return. This horizon is not a physical surface, but a limit beyond which the fabric of space-time is warped so severely that escape becomes impossible, even for light itself. From an outside observer's perspective, anything crossing this threshold appears to slow and fade as gravitational time dilation stretches the passage of time. The event horizon thus serves as a cosmic veil, hiding the singularity and the extreme warping it causes from direct observation. Yet it is precisely this boundary that defines a black hole and challenges our understanding of space and time. In a sense, the event horizon represents the interface between the familiar universe and a realm where classical concepts break down. The study of event horizons has led to profound insights, such as Hawking radiation, which suggests that black holes can emit particles due to quantum effects near the horizon. This discovery hints at a deep connection between gravity, quantum theory, and thermodynamics, opening doors to new physics and stirring questions about information loss and cosmic censorship. Each of these ideas pushes us to reconsider the nature of reality itself. The immense gravity near an event horizon bends space-time in ways that are difficult to visualize, but can be described mathematically through Einstein's field equations. Massive cosmic events, such as the collapse of a star or the merger of massive black holes, lead to dynamic distortions of the surrounding space-time fabric. These distortions create gravitational waves, ripples that travel through the cosmos at the speed of light, carrying information about the cataclysmic events that generated them. The detection of these waves has opened a new window into the universe, allowing us to observe phenomena that were once purely theoretical. As space-time is stretched and compressed, the very geometry of the universe flexes, reminding us that gravity is not merely a force, but a manifestation of curved space-time itself. This curvature dictates the motion of matter and light, guiding planets, stars, and galaxies along their paths. By studying how space-time warps during these massive events, scientists gain insight into the fundamental properties of gravity, including how it behaves under the most extreme conditions imaginable. Approaching the singularity, the warping of space-time intensifies beyond measure, challenging the limits of our current physical theories. Classical general relativity predicts that density and curvature become infinite at this point, but such infinities signal a breakdown in our understanding rather than a physical reality. This enigmatic region invites the development of new, unified theories that integrate quantum mechanics with gravity, aiming to describe the true nature of singularities. Some theoretical models propose that the singularity may be replaced by exotic structures or states of matter, while others suggest that the fabric of space-time itself may transition into a different regime. These ideas remain speculative, but underscore the singularity's role as a frontier where known physics gives way to the unknown. It is this boundary, where space and time cease to behave as we expect, that continues to captivate physicists and philosophers alike. As we deepen our exploration of these extreme boundaries, our understanding of the cosmos and the laws that govern it inevitably evolves. When two black holes approach one another in the vast emptiness of space, their immense gravitational fields begin an intricate cosmic dance. These titanic objects, each containing the mass of several suns compressed into an unimaginably small region, exert powerful pulls that distort the very fabric of space-time around them. As they spiral closer, their gravity interweaves, creating a dynamic curvature that grows more intense with every passing moment. This convergence is not a gentle meeting, but a violent warping of space-time that challenges our finest instruments and theories alike. The collision of these massive bodies releases a tremendous amount of energy, not as light or matter, but as gravitational waves, ripples that propagate through space-time itself, carrying information about the event's magnitude and nature. These waves travel vast distances, subtly stretching and squeezing the universe as they pass, offering a rare glimpse into phenomena that were once purely theoretical. The detection of such waves has opened a new window into the cosmos, allowing scientists to observe the unseen and to test the predictions of Einstein's general relativity in extreme conditions. As black holes collide, the warping of space-time intensifies dramatically, reaching levels where the classical understanding of gravity meets its limits. The violent merger produces a profound disturbance, sending ripples outward at the speed of light. These gravitational waves carry with them the signature of the event, its mass, spin, and the dynamics of the collision, encoded in subtle distortions that can be measured by highly sensitive detectors on Earth. The wave's passage gently expands and contracts the space between atoms, revealing the invisible dance of these cosmic titans. Importantly, the energy released in gravitational waves during such mergers can be greater than the combined light output of all stars in the observable universe at that instant, underscoring the extraordinary power involved. This phenomenon not only confirms the existence of black holes, but also provides direct evidence of the dynamic warping of space-time envisioned by general relativity. It is through these observations that we begin to understand how massive cosmic events influence the structure and evolution of the universe on the grandest scales. surroundings, the ripples generated by colliding black holes traverse the cosmos, interacting subtly with everything they encounter. While imperceptible to human senses, these gravitational waves carry pristine information from regions otherwise shrouded in darkness, untouched by electromagnetic radiation. Their detection requires exquisite precision, achieved by observatories such as LIGO and Virgo, which measure changes in length smaller than a fraction of a proton's diameter. With each new detection, scientists refine their understanding of gravity's role in shaping the cosmos, deepening insights into the life cycles of massive stars and the dynamics of compact objects. Moreover, these waves offer a unique probe into the behavior of space-time under extreme conditions, potentially guiding the development of new theories that reconcile gravity with quantum mechanics. As we continue to listen to the echoes of these monumental collisions, the universe reveals itself as a dynamic tapestry, woven from the very distortions of the space-time fabric. The study of colliding black holes not only illuminates the violent processes that sculpt the cosmos, but also challenges us to expand our comprehension of physical laws. Each event pushes the boundaries of our theoretical frameworks, inviting speculation and discovery. As these massive objects merge, they briefly form a single, more massive black hole before settling into a new equilibrium. This transition involves complex interactions, including the emission of gravitational waves that carry away excess energy and angular momentum. Through detailed analysis of these signals, physicists can infer the properties of the newly formed black hole and test predictions about the nature of gravity in the strong field regime. In this way, colliding black holes serve as natural laboratories for exploring the frontiers of astrophysics and fundamental physics. Such explorations set the stage for understanding other cosmic phenomena where space-time itself is profoundly transformed. Gravity, the invisible force that governs the motion of planets, stars, and galaxies, is far more than a simple attraction between masses. According to Einstein's theory of general relativity, gravity arises from the way massive objects warp the fabric of space-time itself. Imagine space-time as a vast, flexible sheet. When a massive body like a star or black hole presses down on this sheet, it creates a curvature that influences the paths of objects moving nearby. This elegant picture replaces the old notion of gravity as a force acting at a distance, revealing instead a dynamic interplay between matter and the geometry of the universe. When colossal cosmic events occur, such as two black holes spiraling toward each other, the intense warping of space-time can ripple outward, much like waves spreading across a pond. These ripples are what we call gravitational waves, subtle disturbances that travel at the speed of light, carrying information about their cataclysmic origins across the cosmos. The concept of gravitational waves was predicted by Einstein over a century ago, yet their direct detection eluded scientists for decades. It was only in 2015 that the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured the faint signals of merging black holes, confirming a key prediction of general relativity. This discovery was groundbreaking, not only because it opened a new window into observing the universe, but because it confirmed that space-time is indeed a dynamic entity, capable of rippling and vibrating. The waves detected were incredibly subtle, changing the length of LIGO's 4-kilometer arms by less than 1,000th the diameter of a proton. Such precision highlights the remarkable ingenuity and persistence behind this achievement. Through gravitational wave astronomy, we can now listen to the universe in a way that complements traditional light-based observations, revealing phenomena hidden from telescopes and deepening our understanding of the cosmos. These ripples in space-time carry encoded stories of their cataclysmic origins, whether from colliding black holes, neutron star mergers, or perhaps even the echoes of the Big Bang itself. By analyzing the frequency, amplitude, and waveform of gravitational waves, scientists can infer the masses, spins, and distances of the objects involved, offering insights into the most extreme environments in the universe. Moreover, gravitational waves provide a unique testing ground for the laws of physics under conditions impossible to replicate on Earth. They challenge our understanding of gravity in its most intense form and may eventually guide us toward a unified theory that reconciles general relativity with quantum mechanics. As detectors improve and new observatories come online, the symphony of the cosmos will become ever clearer, inviting us to explore deeper mysteries woven into the fabric of space and time. The detection of gravitational waves not only validates decades of theoretical work, but also ushers in a new era of astrophysics, one where the universe reveals itself through subtle vibrations traveling across the cosmic expanse. These waves transform our perception of space-time from a static backdrop into a dynamic stage, alive with the echoes of massive events that shape the universe. In this unfolding narrative, each ripple is a messenger, carrying secrets of creation, destruction, and transformation. As we continue to listen and learn, we prepare to uncover yet more profound phenomena where the very structure of space and time bends, twists, and resonates in response to the colossal forces at play. This journey into the depths of gravitational wave science naturally leads us to consider how these insights intersect with other fundamental aspects of the cosmos. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, stands as a monumental achievement in the quest to understand the fabric of our universe. Designed with extraordinary precision, its twin detectors in Washington and Louisiana are capable of measuring distortions in space-time smaller than a fraction of a proton's diameter. This remarkable sensitivity allows LIGO to capture the faint ripples known as gravitational waves, which are generated by some of the most violent and energetic events in the cosmos. These waves travel vast distances, carrying with them information about phenomena such as the merging of black holes or neutron stars, events that were once purely theoretical. When LIGO first detected these waves in 2015, It provided the first direct evidence that space-time is not a static arena, but a dynamic entity that responds to the movement and interaction of massive bodies. This discovery transformed gravitational waves from a mathematical prediction into an observable reality, opening a new window through which we can observe the universe. The detection of gravitational waves by LIGO did more than confirm Einstein's century-old predictions. It revealed how massive cosmic events physically warp space-time. When two black holes spiral inward and eventually collide, their immense masses cause a dramatic curvature in the surrounding space-time fabric. This curvature oscillates outward as gravitational waves, rippling through space at the speed of light. By analyzing the signals captured by LIGO, scientists can reconstruct the properties of these distant cataclysms, estimating the masses involved, the speed of their merger, and the energy released in the process. These measurements provide unique insights inaccessible through traditional electromagnetic observations. The warping of space-time observed through these waves underscores the intimate connection between mass, energy, and the geometry of the universe. It is a profound testament to the dynamic and interconnected nature of cosmic phenomena, where gravity serves as the sculptor of space and time. Beyond confirming theoretical models, LIGO's detections have enriched our understanding of how gravitational waves traverse the cosmos, carrying with them a story etched into the very structure of space-time. As these waves propagate, they stretch and squeeze the distances between objects, albeit by infinitesimal amounts, revealing that space itself is flexible and responsive. This perspective challenges our everyday intuition, inviting us to imagine the universe not as a rigid stage, but as a living tapestry woven with invisible threads of gravity. These threads are tugged and pulled by massive events, their ripples extending across billions of light years to reach our detectors. Through patient observation and meticulous analysis, we begin to decode this cosmic language, learning about the origins and evolution of stars, black holes, and the galaxies that house them. Each detection enriches a narrative of cosmic change, a universe in motion, and a reality where space-time itself is an active participant in the celestial dance. The remarkable achievement of LIGO serves as a bridge between abstract mathematical concepts and tangible experimental evidence, anchoring our understanding of space-time warping in measurable phenomena. This experimental reality empowers physicists to explore new questions about the fundamental nature of gravity and its role in shaping the large-scale structure of the cosmos. With each new detection, we refine our models and deepen our appreciation for the delicate interplay between mass, energy, and geometry that governs the universe. As gravitational wave astronomy matures, it promises to unveil secrets from epochs long past, illuminating the processes that forged the universe as we know it. This unfolding exploration invites us to consider the broader implications of a universe where space-time is not merely a backdrop, but a dynamic participant, poised to reveal even more profound mysteries in the vast, cosmic expanse. Beyond the pioneering detections of black hole collisions, the cosmos presents other extraordinary events that warp the fabric of space-time in profound ways. One such phenomenon involves the merger of neutron stars, ultra-dense remnants of massive stars that have undergone supernova explosions. These stellar corpses, often no larger than a city, yet containing more mass than our Sun, create some of the most intense gravitational fields in the universe. When two neutron stars spiral toward one another, their gravitational dance accelerates, emitting gravitational waves that ripple outward across the cosmos. This cosmic choreography not only distorts space-time, but also releases a burst of energy, detectable by instruments like LIGO and Virgo, allowing us to witness the dynamic interplay of gravity on a scale both immense and intimate. The significance of neutron star mergers extends beyond their gravitational wave signatures. These cataclysmic events are also responsible for forging heavy elements, such as gold and platinum, through rapid neutron capture processes during their violent collisions. As these stars coalesce, the intense warping of space-time becomes a laboratory for studying the behavior of matter under extreme conditions, unattainable on Earth. The distortions caused by such mergers challenge our understanding of gravity, pushing the predictions of Einstein's general relativity to its limits. Observations of these events provide unique insights into the equation of state of neutron star matter, enhancing our comprehension of how gravity influences matter at nuclear densities. Neutron star mergers also highlight the dynamic and interconnected nature of cosmic phenomena. The gravitational waves they produce travel vast distances, gently stretching and compressing space-time itself as they pass through our detectors. These ripples carry with them information about the masses, spins, and orbital dynamics of the merging stars, acting as messengers from the distant universe. In addition, the warping of space-time during these events can affect the surrounding environment, triggering electromagnetic emissions such as gamma-ray bursts and kilonovae. This interplay between gravity and electromagnetic signals enriches our narrative of cosmic evolution, revealing gravity not as a static force, but as an active, shaping presence, capable of influencing matter and energy across billions of light years. As we continue to observe neutron star mergers alongside other massive cosmic events, such as black hole collisions and supernova explosions, our understanding of how gravity sculpts the universe deepens. Each detection serves as a new chapter in the story of space-time, illustrating how the geometry of the cosmos responds to the presence and motion of mass and energy. These remarkable events remind us that gravity, while subtle in everyday life, is a fundamental architect of cosmic structure and transformation. With every ripple recorded and every signal analyzed, we edge closer to unraveling the profound mysteries embedded in the very fabric of space and time, inviting us to explore further the extraordinary ways in which the universe reveals its hidden dimensions. When we consider the nature of gravity in the context of massive cosmic events, it becomes clear that gravity does more than simply pull objects together. According to Einstein's theory of general relativity, gravity is the manifestation of mass and energy curving the fabric of space-time itself. This curvature alters the path that particles and light follow as they travel through the cosmos. Light, which ordinarily moves in straight lines, finds its trajectory bent when passing near extremely massive objects, such as black holes, neutron stars, or galaxies. This bending of light by gravity is not just a theoretical prediction, but a phenomenon we have observed repeatedly, revealing the profound influence gravity exerts on the universe. One of the most mesmerizing results of this space-time warping is gravitational lensing, a cosmic spectacle where the light from distant stars or galaxies is deflected around massive objects between the source and the observer. This effect acts much like a natural lens, magnifying and distorting the images of background objects. Depending on the alignment and mass of the intervening body, gravitational lensing can create multiple images, arcs, or even complete rings known as Einstein rings. These stunning visuals not only provide breathtaking views of the universe, but also serve as powerful tools for astronomers. By studying the patterns of light bending, scientists can infer the presence of otherwise invisible matter, such as dark matter, and map the distribution of mass throughout the cosmos. The subtle warping of spacetime that causes gravitational lensing is a testament to the interconnectedness of mass, energy, and light. In regions where gravity is extraordinarily strong, light may even be trapped or delayed, offering glimpses into the extreme conditions near black holes or merging neutron stars. These distortions challenge our perceptions of space and time, reminding us that the universe is a dynamic, ever-changing tapestry woven from the interplay of fundamental forces. Observations of gravitational lensing continue to enrich our understanding of cosmic evolution, revealing how massive structures grow and interact over billions of years. As our instruments become more sensitive, the ability to detect and interpret these subtle shifts in light's journey brings us closer to unlocking the secrets hidden within the depths of space. The phenomenon of space-time warping provides astronomers with a remarkable natural tool to peer into the depths of the cosmos. When massive objects such as galaxy clusters or black holes distort the fabric of spacetime, they create what is known as gravitational lensing. This effect bends and magnifies the light from objects lying far behind these massive foreground structures, allowing distant galaxies, otherwise too faint or obscured, to become visible. By analyzing the patterns and distortions in the lensed images, researchers can map the distribution of mass in the universe, including the elusive dark matter that neither emits nor absorbs light. This method unveils a hidden scaffolding that shapes the large-scale structure of the cosmos, revealing how matter clumps together and evolves over billions of years. Beyond revealing distant galaxies, the warping of spacetime also serves as a cosmic magnifying glass, enabling detailed studies of objects at the edge of observable space. As light rays curve around massive objects, They follow elongated or multiple paths, resulting in arcs or multiple images of the same source. Such phenomena not only confirm the predictions of Einstein's theory of general relativity, but also help astronomers measure the expansion rate of the universe with increasing precision. Observing these subtle shifts in light's trajectory allows scientists to investigate the properties of dark energy, the mysterious force driving the accelerated expansion of the universe. Each warped image acts as a messenger from the distant past, carrying information encoded in its distorted light about the composition and behavior of the universe across cosmic time. The study of space-time warping extends beyond visible light, encompassing observations in radio waves, X-rays, and other electromagnetic spectra. By combining data from different wavelengths, astronomers gain a multi-dimensional view of cosmic phenomena, from the swirling gas around supermassive black holes to the faint glow of primordial galaxies. Gravitational lensing also offers a window into the dynamics of galaxy clusters, where the distribution of dark matter and ordinary matter can be disentangled. This intricate interplay between gravity and light challenges our understanding of fundamental physics and propels the development of advanced models and technologies. As telescopes and detectors grow ever more sophisticated, the ability to read the subtle imprints of space-time warping promises to illuminate the darkest corners of the universe. In this ongoing journey of discovery, the warping of space-time serves as a bridge between theory and observation, linking the gravitational dance of massive bodies to the light that reaches our instruments. Through careful measurement and analysis, astronomers continue to unravel the mysteries of cosmic evolution, tracing the growth of galaxies, the behavior of dark matter, and the influence of dark energy. Each new observation deepens our appreciation for the intricate and dynamic cosmos, where the fabric of space and time is not static, but a living canvas shaped by mass and energy. This profound connection invites us to explore further, seeking new insights and expanding the horizons of human knowledge. Gravity, the subtle yet all-pervasive force, continues to captivate scientists as they delve deeper into its fundamental nature. It is gravity that governs the motion of planets, the orbits of stars, and the vast structure of the cosmos itself. Yet, despite its familiarity, gravity remains one of the most enigmatic forces in physics. The theory of general relativity, formulated by Einstein over a century ago, revealed that massive objects warp the very fabric of space-time, bending it much like a heavy weight distorts a stretched sheet. This curvature guides the motion of objects and even the path of light, giving rise to phenomena such as gravitational lensing and black holes. However, as we probe scales both immense and infinitesimally small, the classical description of gravity encounters challenges, suggesting that a deeper, more unified understanding awaits discovery. Massive cosmic events act as natural laboratories for exploring the behavior of gravity under extreme conditions. When two black holes spiral inward and merge, or when neutron stars collide in a cataclysmic burst, the resulting ripples in space-time, known as gravitational waves, carry invaluable information across the universe. These faint echoes, first directly detected only in recent years, have opened a new window onto the cosmos, allowing us to observe phenomena invisible to conventional telescopes. By studying these waves, scientists gain insights into the warping of space-time at its most intense, testing the limits of general relativity and exploring the properties of matter under unimaginable pressures. Each detection enriches our understanding and pushes the boundaries of what is known about gravity's role in shaping cosmic history. Beyond observational breakthroughs, theoretical research strives to reconcile gravity with the principles of quantum mechanics, the framework governing the subatomic world. The quest for a quantum theory of gravity aims to describe how gravity operates at the smallest scales, where space-time might exhibit a granular or fluctuating nature. This endeavor challenges foundational concepts and requires innovative approaches, from string theory to loop quantum gravity, each offering glimpses into a more complete picture of reality. As experiments and observations advance, they provide crucial clues that may guide researchers toward a synthesis of the macroscopic and microscopic realms. This pursuit not only deepens our grasp of gravity itself, but also promises to illuminate the origins of the universe and the fundamental workings of nature. The ongoing exploration of gravity's mysteries invites us to contemplate a universe far richer and more intricate than once imagined. With each new discovery, the interplay between mass, energy, and the geometry of space-time reveals layers of complexity and beauty. As technology evolves and our observational reach extends, future research will undoubtedly uncover phenomena yet unimagined, bringing us closer to a unified understanding of the cosmos. This unfolding story of gravity is a testament to human curiosity and the enduring desire to comprehend the forces that shape existence itself. Gravity, though invisible to the eye, is a fundamental force that governs the motion of everything, from the smallest particles to the largest cosmic structures. It is the quiet architect behind the orbits of planets, the dance of galaxies, and the evolution of the universe itself. When massive cosmic events occur, such as the collision of black holes or the explosion of supernovae, they produce ripples in the fabric of space-time, distorting it in ways that challenge our deepest understanding of reality. These warps and waves, predicted by Einstein's theory of general relativity, reveal that gravity is not merely a force pulling objects together, but a dynamic interaction shaping the very geometry of the cosmos. By studying these phenomena, scientists can peer into conditions so extreme that they push the boundaries of known physics, providing insights into the origins and fate of the universe. The significance of understanding gravity extends beyond the vastness of space and time. It also profoundly influences the technologies we rely upon daily. GPS satellites, for example, must account for the subtle warping of space-time caused by Earth's mass to provide accurate positioning data. Without correcting for gravitational time dilation, our navigation systems would quickly become unreliable, underscoring how cosmic principles directly affect modern life. Similarly, advances in gravitational wave detection have opened a new window into the universe, allowing us to observe events billions of light years away through the faint tremors they send across space-time. These breakthroughs not only deepen our cosmic perspective, but also drive innovations in sensor technology and data processing, which can have far-reaching applications here on Earth.
Looking forward, the study of gravity promises to be a cornerstone of future space exploration and scientific discovery. As humanity endeavors to journey farther into the cosmos, understanding how gravity shapes environments, from the gentle pull of our moon to the intense gravity wells near neutron stars, will be essential for navigation, habitat design, and safety. Moreover, unraveling gravity's mysteries may unlock new methods of propulsion or energy generation, potentially transforming how we travel and survive in space. The ability to predict and harness the effects of gravitational fields could enable missions to previously unreachable destinations and deepen our comprehension of the cosmic tapestry. Each step forward in gravitational research brings us closer to bridging the gap between the immense scale of the universe and our place within it. Gravity quietly weaves the fabric of our universe, an invisible force that guides the dance of celestial bodies across the vast cosmic stage. It is the unseen architect that sculpts galaxies, clusters, and the intricate web of space-time itself. When massive events occur, such as the collision of black holes or the explosive death of stars, gravity bends and warps the very geometry of space and time, reshaping the cosmos in profound ways. These ripples in the fabric of space-time, known as gravitational waves, travel through the universe, carrying with them stories from the most powerful and distant phenomena. Through these subtle distortions, we gain glimpses into realms far beyond our reach, deepening our understanding of both the universe's majestic scale and the delicate forces that govern it. The warping of space-time caused by massive cosmic events is not merely a spectacle of nature, but a fundamental aspect of how gravity operates. Einstein's theory of general relativity revealed that gravity is not just a force pulling objects together, but a curvature of space-time itself. This curvature directs the motion of planets, stars, and light, leading to phenomena such as gravitational lensing, where light bends around massive objects like galaxies. Such effects allow astronomers to peer into hidden regions of the universe, unveiling structures and events otherwise invisible. The interplay between mass, energy, and the shape of space-time demonstrates that gravity is a dynamic participant in the cosmic story, continuously shaping and reshaping the universe in subtle yet powerful ways. As we reflect on gravity's role, it becomes clear that this force is much more than a scientific concept. It is a profound connection that links all matter and energy across the cosmos. Gravity's influence extends from the smallest particles to the largest galactic superclusters, binding the universe into a coherent whole.
It orchestrates the cycles of star birth and death, the formation of planets, and the rhythms of cosmic evolution. In this vast and ever-changing universe, gravity is the silent rhythm that underlies every motion, every orbit, every cosmic event. Understanding gravity is, in many ways, understanding our place in this grand cosmic story. A story that continues to unfold with every observation, every discovery, and every moment of quiet contemplation beneath the stars. In embracing gravity as the invisible architect of the universe, we recognize a force that is both familiar and mysterious, constant yet full of surprises. It invites us to explore not only the outer reaches of space, but also the depths of fundamental physics, bridging the gap between the tangible and the abstract. As our knowledge grows, so too does our appreciation for the profound elegance with which gravity shapes reality, guiding the endless unfolding of cosmic history. In this way, gravity connects us intimately to the universe, reminding us that though we are small, we are part of a vast and beautiful cosmic dance, choreographed by this gentle, persistent force.